guys, it's Olivia. Welcome to your endocrinology chapter. In this chapter, we're going to be going over a lot of the different hormone systems that are very integral to different parts of your body and are highly likely to show up on step 1. First, we'll cover our general principles. We'll go through different types of signaling. Then we'll talk about different classifications of hormones themselves. Then we'll kind of meet the team and we'll talk about all the different glands that are involved in our endocrine system, their location and their function. Then finally, we'll talk about feedback loops. And these are going to be very important to understand before we can apply our knowledge about hormones to the body system. So we'll talk about negative and positive feedback loops, and both of these will help you answer questions on step 1. Okay, now let's talk about some general principles of endocrinology. So first, we'll cover the different types of signaling. And the first type of signaling that I want to make sure that you're aware of is autocrine signaling. This root auto means self. So if I'm talking about an autobiography, that is going to be a biography about myself. If we are talking about autophagy, that is going to be a cell eating itself. Similarly here, we are talking about autocrine signaling. So that is going to be a cell that is signaling itself. And I think a great example of this would be something like if a cell releases caspase internally, that's a way a cell can signal itself to carry out an action, in this case, apoptosis. So that is a great example of autocrine signaling. Now, the next type of signaling that I want to talk about is paracrine signaling. And para, this root here, means nearby or beside. So if you do something peri-procedurally or an event occurred peri-procedurally, that means that event occurred near the procedure, beside the procedure in time. Similarly here, when we're talking about paracrine signaling, we are talking about cells that are signaling cells that are right beside them. And a great example of this would be something like D cells in the stomach who are releasing somatostatin. Somatostatin is going to signal our G cells that are right beside our D cells, and it's going to inhibit them from secreting gastrin. That's a pretty local response, though. That somatostatin, symbolized by these triangles here, doesn't really have very far to travel, and so that is going to be an example of paracrine signaling because we are signaling cells that are right beside our original cell. In contrast, in endocrine signaling, we are going to be signaling cells that are very far away from our original cell that is releasing the molecule. Endo means inside, so it's not going to be very helpful for helping us remember what's happening. But when you think about endocrine signaling, I want you to think about your classic hormone being released. It's usually hormones that are going to be released that are going to hop on our expressway or our highway, which is the vasculature. The vasculature, or the blood vessels, are our body's way of transporting substances throughout the entire body. So our little hormone here is going to hitch a ride with our vasculature, and it is going to travel to a part of the body that might be incredibly far away from the original cell where it was made in. And then this molecule is going to signal our cell in this other part of the body to affect a response. And that is the difference between endocrine and paracrine signaling. In endocrine signaling, we are traveling very, very far away, maybe to a different region of the body, usually through the vasculature. And in paracrine signaling, we are signaling cells that are very close, within the same organ at least. And that is the difference. The distance traveled is the difference here. Now, the last type of signaling that I want to make sure that you guys are aware of is exocrine signaling. So exocrine glands, whenever I think about an exocrine gland, I think about it producing something that is going to exit the body, exocrine and exit. And these glands are really producing substances that are going to be secreted outside the body. So they're going to exit the body. Examples of this might be sweat, milk, saliva. If you look over here, you can see we have our classic hair follicle with this little sweat gland that is preparing to excrete that substance outside of the body. And that is going to be the definition of our exocrine gland. We're making something that is going to exit the body. So those are our different types of glands. Now let's dive into the different types of hormones. Remember, this is the endocrine chapter, so we're going to be talking about endocrine signaling, and endocrine signaling occurs primarily through the help of hormones. So when we talk about a hormone, what is a hormone? Well, a hormone is a signaling molecule that travels through the body to target distant cells. Now, there are several types of hormones that exist and can perform endocrine signaling. So let's go through those now. First, let's talk about our protein and peptide hormones. These are exactly like they sound. They are just proteins that act as hormones. So like all proteins, they are made from amino acids, multiple amino acids linked in a chain. These proteins are often packaged in hydrophilic vesicles. Remember, hydrophilic means that they like the water, so they will be highly soluble in our blood, which is traveling on our vasculature expressway. And these hydrophilic vesicles will travel through the bloodstream really well. However, what they're not going to be able to travel through is the cell membrane. Remember, our cell membrane is made up of a lot of phospholipids, so it is going to be very hydrophobic. And we have something that is hydrophilic, like our proteins, that is not going to be able to traverse that membrane very well. So it's not going to be able to get inside our cell. That does not stop the protein hormones, however, from exerting their effects. Our protein hormones are going to exert their effects through membrane-bound receptor signaling. And that should make sense to you. If our protein hormones can't go inside the cell, they're going to have to signal the cell in another way. And the way they do that is by knocking on the door saying, hey, we've got a message for you. We can't come inside, but we can bind to these receptor molecules on the surface of the cell. Here, this would be a great example of that, and exert our effects that way. Some protein hormones that you might be familiar with, insulin or oxytocin, are going to signal cells this way. So if you look over here, this might be a little insulin triangle binding to maybe a tyrosine kinase receptor and then exerting additional effects within the cell. Now, the next type of hormone that I want to make sure you're aware of are our amino acid derivatives. And I know this sounds very similar to a protein or peptide hormone in that they both are made of amino acids, but the difference here is that these are going to be made from single amino acids, so just one. Our protein hormones are amino acids in a very long chain. They are full proteins. These are only one amino acid that has been converted into a hormone. And one amino acid that this happens to a lot is tyrosine. Tyrosine can be converted into thyroxine, so one of your thyroid hormones. Now, the next type of hormone that you should be aware of are our steroid hormones. Steroids are all going to be derived from cholesterol. So if you look over here, we have this molecule of cholesterol. And you can see that we have the classic 4 rings that are going to be in pretty much every single steroid molecule. And if you ever see these 4 rings, you should immediately be thinking like, oh, that might be a steroid if you're faced with that in a question. Steroids, because they are made from cholesterol, are going to be lipophilic. And because they are lipophilic, that's kind of the opposite of how proteins are, right? Remember, our proteins were hydrophilic, so they had a problem bypassing the cell membrane. Our steroids, by contrast, are going to be lipophilic, so they have increased ability to traverse the cell membrane, and that is going to make them prime candidates for intracellular binding. They will bind these intracellular nuclear receptors. If you look over here, you can see our little steroid molecule is going to be binding to this intracellular receptor. That receptor oftentimes will translocate into the nucleus to exert its effects. So our steroids are going to be binding intracellularly most of the time. And examples of our steroids are a lot of times our sex hormones, so like estradiol, testosterone, and also cortisol as well. It's going to be a huge one to be aware of. And all of these are going to be binding intracellularly. Now, our next big group of hormones are our eicosanoids. And our eicosanoids are going to be derived from fatty acids, most often arachidonic acid. And you might be familiar with these if you remember back to this pathway that you probably learned about in hematology. We have arachidonic acid at the top, and this arachidonic acid is going to be converted by either COX-1 or COX-2 into different hormones. And then, of course, we have our NSAIDs or our COX inhibitors that are going to impact this pathway, but that's beyond the scope of this video. In this video, what I want you to know is that our eicosanoids are going to be all of these different hormones down here that are derived from arachidonic acid, and all of our eicosanoids are going to be binding to these membrane-bound receptors. So similar to insulin, they are also going to be binding at our membrane-bound receptor over here. And examples of these would be things like prostaglandin, thromboxane, all of those things that are derived from arachidonic acid. Now, our final group of hormones here, and I think the one that is the least intuitive to think about as a hormone, are our gases. But gases can be hormones as well. Gases are small molecules, they're really tiny. They often can diffuse across the cell membranes without any help. And examples of gases that are hormones are going to be things like nitrous oxide, ethylene, and they can travel through the bloodstream as well to get to distant targets. So that was a general overview of our general principles of endocrinology. Let's quickly review what we just talked about. There are 4 kinds of signaling: autocrine signaling, in which a cell signals itself; paracrine signaling, where we signal nearby cells; endocrine signaling, where we signal far away cells; and then exocrine signaling, where we make things to leave the body. Then we have our different classifications of hormones. Hormones, of course, are going to be involved with our endocrine signaling. We have our protein hormones or peptide hormones. Those are going to be proteins that are usually binding at our extracellular receptors. Then we have our amino acid derivatives made from just one amino acid, a single amino acid. Next, we have our steroids. Our steroids are always going to have these 4 rings and are usually going to be binding intracellularly, not extracellularly. Then we have our eicosanoids, all derived from arachidonic acid, and these eicosanoids are going to be things like prostaglandin or thromboxane. And then finally, we have our gases, which are tiny molecules that can easily diffuse across the cell membrane, most notably nitrous oxide. So we've made it through a general overview of some of the principles in endocrinology. Now let's try a practice question. So something they might ask you on step 1 would be a question like, where in the cell does dinoprostone exert its effects? And how you would answer this question is first you would say, okay, what is dinoprostone? Prostone, as you might know, is basically PGE2. And PGE2 can be used in the medical setting for things like dilating the cervix or inducing labor, maybe maintaining a patent ductus arteriosus, but that's not what the question is asking you. The question is asking you, where does PGE2 act in the cell? Where does dinoprostone act in the cell? Well, because you watched this video and you know that PGE2 is an eicosanoid hormone, you know that eicosanoid hormones bind to membrane-bound receptors outside the cell, so membrane-bound receptors outside the cell, and you'll be able to answer this question knowing that PGE2, as an eicosanoid, will also bind outside the cell to a membrane-bound receptor. Now that's all I have for you on principles of general endocrinology. I hope this video is helpful, and I'll see you next time.